All right, hey everybody. Welcome back to Math Background for Machine Learning. So I figured I would start class today by going over our solution to the Fisher discriminant exercise from last time. So this is posted on Piazza so everybody can take a look at it. And please, as always, ask questions and we'll try and answer them. All right, so I guess we can start by looking at the plot, right? So we asked you to plot the positive examples, which are these ones at the corners of a square, and the negative examples, which are these ones closer to the origin, as well as to compute and plot the decision boundary, which is this circle here. So I should point out that just by looking at the feature function, it should be possible to figure out that the decision boundary is going to be a circle because it's got, so the feature function was x, y, x squared, and y squared. And so you're going to wind up getting that the discriminant function is a quadratic function equal to 0, and the coefficients of the quadratic term in x and y are going to be the same, and so you're going to get a circle as your decision boundary, right? The solutions to quadratic equations are always either circles, ellipses, parabolas, or hyperbolas, and depending on the structure of the coefficients, you can tell which one's going to be which. So you can sketch this by hand if you like, or we provide some code to make this plot here. So here are, I've included the correct values of the coefficients of the discriminant function, w, and the intercept term b. But let's take a look at the code to see how those were calculated. So I guess, so first we can start with the given information. This is copied directly from the problem statement. Then we can calculate the feature function applied to each of our data points. So this right here, x plus and y plus are two row vectors corresponding to the x and y coordinates of the positive examples, and similarly for x minus and y minus for the negative examples. So this line here gives x, y, x squared, and y squared for the positive examples. So this calculates our feature function that we gave in the problem description. So you can see, well, so for people who aren't familiar with MATLAB, semicolon means to stack matrices on top of one another. So x is a row vector, x plus is a row vector that gives you the first row of the matrix, y is the next row of the matrix, x squared is the one after that, and y squared is the one after that. And then the same code for the negative examples. And then so the hint said to start off by calculating the conditional expectations of the feature function, and so that's what these two lines do. For all of the positive examples, right, the conditional distribution over the positive examples is just equal weight on each of those. That was given in the problem statement as well. And so the expectation is the same as just the mean, the average. And so this takes the mean along one coordinate of a matrix to get you the average feature function. The same thing for the negative examples. And then these equations, the definitions of W and B, we just gave them to you in the notes. And in the notes, we mentioned that what this gives you is the perpendicular bisector between the two class means, right? So one class mean, the other class mean. And these equations calculate the perpendicular bisector. And again, if that doesn't seem obvious from the equations, it's good to work out and convince yourself that that's the case. And so that's the answer, right? We calculate, we start from the given coordinates, we calculate the feature functions, calculate the means, conditional on being positive or negative, and then we just use the equations from the notes to calculate W and B. And then this here, this is very MATLAB specific, so if you don't follow this if you don't follow this way of making a plot, that doesn't matter. What it's doing is evaluating our discriminant function on a grid of points and then making a contour plot to find where the discriminant function crosses 0. And you know, the code would look different, but you could do exactly the same thing in any of the languages that we've discussed in this course. All right, so that's the exercise solution. Looks like nobody has added questions for it on Piazza yet, but feel free to do that, and we'll try and answer those. All right, so the next thing I wanted to do was go back to our lecture notes. Oh, I should say, there is a question on Piazza that I wanted to remember to answer, which is whether we're going to have homework this week. The answer is, of course. So we are close to releasing both homework 2 and the next short problem set. We will give you details on those when they're available, but they could be released as early as tonight. So you know, be on the lookout for those. All right, so let's go back to our notes. So we went over this first section here, but just to summarize, we're going to be talking for this class about functions that map vectors in one vector space to vectors in another vector space. Those could be real vector spaces like, you know, R3 or R5, or they could be other vector spaces like the crazy ones we've talked about, vectors where vector spaces where the vectors are things like real valued functions, or where they're linear combinations of trees, right? And so there are a few examples, and just to reiterate, when there's a lot of vector spaces floating around, it's a good idea to, in your head, type check any expression that we write down, because that can help you, so if you write down the expression, it can help you catch an error, right? Maybe you wrote something in the wrong order, and if you type check it, you'll catch that mistake. And if you're trying to understand an expression that somebody else wrote down, it can help to type check it so that you just know which vector space each one of the intermediate quantities is in. Right, and by type checking, I mean exactly that. Just go through the expression, look at all of the sub-expressions, and write down for yourself, or you know, just think in your head, what type, what vector space is each one of the intermediate quantities. And sometimes it also helps to ask yourself, like, what is the type of each one of the functions, right? So you could have some complicated definition of a function, and it helps to think, what vector space does it take as input? Or possibly if it takes more than one argument, what vector spaces does it take as input? And then on the other end, what does it provide as output? All right. So just a little bit of vocabulary is that real valued functions, you know, functions from a vector space V to the real numbers, are often called functionals. A functional is a function. It's just, if you want to specify that it's real valued, you can say that. And then a function from one vector space to another is often called an operator. And so a functional is also an operator, right? Because the real numbers themselves form a vector space. But usually when you say an operator, you mean, you know, some other more complicated vector space that you map from and to. So that's just a little bit of vocabulary. We're going to be looking particularly at linear functions, or linear functionals, or linear operators. So what is a linear function? It just means that if you have the function applied to ax plus by, where x and y are vectors and a and b are scalars, meaning real numbers, that f of ax plus by is equal to a times f of x plus b times f of y, right? So linearity just means that you can pull out addition and scalar multiplication outside the function. There are a few well-known examples. So linearity is really useful because it helps you work with expressions involving functions, and so it's good to have some examples in mind. One example is multiplication by a matrix. So if you have f of x equals a times x, then f of ax plus by is a times ax plus by, and you can pull out the scalar multiplication and the addition through your matrix multiplication. As a special case of that one, dot product is a linear function, and in fact a linear functional because it's real valued. Right, so dot product with a fixed vector w, the function w dot x is linear. So we saw an example of that, for example, with linear discriminant functions. And another one that's maybe less well known is the derivative operator. So if you take d by dx that operates on some functions that are differentiable, some real valued differentiable functions, it's true that d by dx of af plus bg, where f is a function and g is a function and a and b are real numbers, you can move that inside and get a d by dx of f plus b d by dx of g. Right, and so this is a nice example because it's a linear function that operates on an infinite dimensional vector space, namely a vector space of functions. All right, so in order to work with linear functions, it's going to help to use what's called a coordinate representation of our vectors. So far, we've been thinking of vectors as a sort of an opaque data type. It's an object. You don't know what kind of object it is. All you know is that it supports adding two vectors together and multiplying a vector by a scalar, right? So, and in particular, the vector could be something weird that you otherwise wouldn't know how to work with, right? If you don't know whether it's a function or a tree, it's hard to think what other operations you could be guaranteed to do on it. All right, and that's in contrast to what you were probably first taught for vector spaces, where vectors were tuples of numbers, tuples in Rn, right? A tuple of n real numbers. And so that you would have, specifically in the vector, you would have an additional operation, which is to take the, let's say, fourth coordinate of the vector, right? And that operation is called indexing. So the first view is called coordinate free or abstract, and the second view is called concrete or coordinate based. And the abstract view of vectors is most useful for thinking about them because there's sort of, if you have a very small number of operations that you can do on a particular data type, it makes it easier to reason about what sorts of things you can do with that data type. But of course, whenever we want to put our vectors in a computer, we're almost always going to do it in terms of a list of coordinates. And so we can go from abstract to concrete. And to do that, we use a basis, right? So we said before that we can take any vector x and express it uniquely as a linear combination of basis vectors, right? So x is equal to a sum of x tilde I times bi, right? So bi is one of your basis vectors, and x tilde I is a real number. And so we take that list of real numbers as coordinates, right? So if x is a vector in V, and V is n-dimensional, we have a basis with n elements in it, then the vector x1 through x tilde 1 through x tilde n is going to be a member of the real vector space Rn. And these two representations, we can think of them as representing the same thing, right? They are not the same thing, right? One is a vector in V and the other is a vector in Rn, but we can go back and forth between them however often we like. And as an illustration that they're not the same thing, imagine what would happen if we picked a different basis, capital B prime, right, with a different set of basis vectors. This coordinate representation would completely change, potentially. And so, but it would not change x at all, right? And so given a basis, we can make a correspondence between V and Rn, but that correspondence depends on which basis we pick. Let's see. So in addition to representations of vectors, it makes sense to have a coordinate representation for linear operators. And it turns out that we don't have to do this separately. Once we've fixed coordinate representations for our vectors, that tells us what coordinate representation to use for our matrices. And so let's work through that. So we have two vector spaces, U and V, and we have a linear operator L that maps from U to V. And we have a basis for U and a basis for V, and we're going to call B1 through Bn the basis for U, and C1 through Cm, right, the basis for V. They don't have to be the same dimension. All right, so we can take one of our vectors Bj that's in U and apply the linear operator L to it. And by definition, if we apply L to an element of U, we'll get an element of V. So the result is, we'll just call it LBJ. And this result, we can expand it in terms of our basis for V. We haven't said how to do that, but we know that there's a unique way to do it. And so we'll get an equation that looks like this. LBJ, this result of applying L to a basis vector in U, we can write it as a linear combination of C1 through Cm. And we're going to give a name to the coordinates in that base, to the coefficients in that basis representation. We'll call them L tilde, 1j, 2j, up to mj. Right? And if we do that for all possible bj from 1 to n, we'll get a matrix, an m by n matrix, whose L tilde ij is a generic element. And what that will mean is that it's the coefficient of Ci in the representation of L times Bj, or L applied to Bj. And so that gives us now a matrix of numbers, and we're going to take that matrix and we're going to call it the coordinate representation of our operator L, right? And as I mentioned before, once we chose the basis for U and the basis for V, we are now, we didn't have to make any further choices in order to get this coordinate representation of L. And the reason we choose this particular coordinate representation is that it agrees with our usual idea of multiplication of a matrix by a vector. In particular, if we take a vector x that has some coordinate representation here, we'll call the coordinates x tilde, and if we multiply, if we apply the operator L to x, right? So this step here, we're just expanding. We know that x has a representation, which is sum of x tilde j times bj. And then by linearity, we can move the linear operator L inside the addition and scalar multiplication. And so we'll get sum from j equals 1 to n of the scalar x tilde j times L bj, right? And then when we expand L bj, right, we know this is the equation for L bj, right? And so this is, we get a sum from I equals 1 to, so this is the sum from j equals 1 to n, and now we get a sum I've switched the limits here. I'll fix that. This upper limit, oh no, I haven't. No, this is fine. So I switched them here in this this one, right? The j sum should go up to n, and the I sum should go up to m, right? And so I'll fix that after class, sorry about that. But we can just take this expression, right, and expand LBJ, and we get the I sum here, and we get this this expression inside, right? And so what this is telling us is that we now have an expression of L times X in terms of multiples of Ci. And so we want the coefficient of Ci is, which is the sum of j, xj, x tilde j times Lij, right? And that is the outcome of matrix multiplication, right? So what we've derived here in this this short section, right, is just that if we take a linear operator and apply it to a vector x, then the outcome is this, right? If we express it in terms of the basis C, C1 through Cm. And the coefficients in that basis are the same as we would get by taking the coordinate representation of x and multiplying it by the coordinate representation of L, right? So let me, I think I wrote that here. Yes, right. So if we have L times x, L applied to x equals y, where x and y are vectors in u and v, and L is a linear operator, that's the same as L tilde times x tilde equals y tilde, where here x tilde and y tilde are real vectors that are the coordinate representations of x and y, and L tilde is a real matrix that's the coordinate representation of L, right? So, so just to summarize, the point of this section here is to say that once we have a coordinate representation for vectors, we can define a coordinate representation for matrices. And the way we do that is by making it so that matrix multiplication should have the same effect as applying the linear function. All right. So let me switch here. There's a little bit more left. We're about halfway through this set of lecture notes, but I wanted to switch briefly to a different set of lecture notes that is also available from Piazza and talk about how to find these coordinate representations for vectors, right? So I said before, we know that there's a unique way to do it, but it helps to be able to computationally find this representation. And so I posted this set of notes that talks about how to do that. All right, so our problem is that we have a vector space V and a basis B1 through Bn for our vector space V, and we have some vector x that is in V, and we know that x has a unique representation, sum from I equals 1 to n, x tilde I times Bi. And we would like to be able to find this representation given x and b, right? So in other words, we want to calculate the coordinates x tilde. And so the way we're going to do that, so we have a question on Piazza about what exactly is a basis. So this is, we discussed this in one of the previous sets of lecture notes, but briefly, a basis is, all right, so we talked about linear combinations of vectors, right? So a linear combination of vectors is like sum of a scalar I, like for a linear combination of these, Bi would be something that looks like this, sum from I equals 1 to n of a scalar I times Bi. Our set B is linearly dependent if we can make 0 as a linear combination of the vectors without setting all of the coordinates to 0, without setting all of the coefficients to 0. So linearly dependent means that you can make 0 as a linear combination. Linearly independent means that you can't. So there's no way to make 0 as a linear combination of our vectors except by setting all of the coefficients to 0. A basis is a linearly independent set of vectors which satisfies one additional property, which is that you can't make it any bigger. In other words, if you add another vector to the set, it's going to be linearly dependent, right? So you take another vector v, and if you add it to the set, another vector, let's call it bn plus 1, and it has to be in our vector space v, and if we add it to our set, then the set becomes linearly dependent, right? So saying that in a shorter way, a basis is a maximal, meaning largest possible, linearly independent set of vectors in our vector space. And the important property of a basis is this one. Every vector in our vector space has a unique representation as a linear combination of basis vectors. A good example of a basis would be in Rn, right? So here's, right, so we have, if we take v equals R3, let's say, then we could take B to be the set of coordinate vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And you can verify for yourself, if you like, that any vector in R3 you can take as a linear combination of these vectors. As a matter of fact, you just take the first coordinate times this vector, second coordinate times that vector, and the third coordinate times that vector. And if you were to add any other vector to this set, it would become linearly dependent. All right. Another basis, right, we could just as well take a different basis, which would be 1, 1, 0, 1, 0, 1, and 0, 1, 1, right? So I'll call that B prime, right? And both of those are bases for R3. And then let's see, a good example of a linear operator on R3 would be the identity function, right? It would take a vector in and give you the same vector back as output. And the coordinate representation, right? So I is in the set of functions from, we'll call it I3, and it's in the set of functions from R3 to R3, right? And it's defined by I3 of x is equal to x for all x. And the coordinate representation of that in basis B, right, we'll put a tilde over it to indicate coordinate representation. Excuse me. The coordinate representation of I3 is just the diagonal matrix with 1s on the main diagonal and 0s elsewhere, right? So that's an example of a basis and the coordinate representation of a linear operator in that basis. I'm not going to try and work out in my head what the representation in B prime is, but that's a short piece of code in MATLAB or Python, and so it would be interesting to oh, well, actually, no. It's going to be actually exactly the same, right? In B prime, I tilde 3 is actually going to be the same thing. So maybe that's not the most interesting example, but you could take other linear operators that would have a different representation in these two bases. All right. Cool. Okay, so we have our vector space, and we know that every vector x has a unique representation in this vector space. as a linear combination of the basis vectors. And so what we want to do is calculate what are the coordinates in this representation. And so in order to find those coordinates, what we're going to do is write down a system of linear equations that the coordinates have to satisfy. And we will then solve the system to find these desired coordinates. And to do that, what we're going to do is just take the dot product, the inner product between our vector x that we want to represent and one of the basis vectors. Each one, we're going to do it separately, but let's take one of them that we'll call bj, right? And so the inner product between x and bj is this, right? And you can, that follows here by linearity, right? So if we just write x inner product with bj is equal to inner product sum over I x tilde I bi inner product with bj, right? That's not a parenthesis, but inner product, an angle bracket. And then by linearity, we can just pull out the addition and scalar multiplication. So we get sum over I x tilde I inner product bi bj, right? So that's this expression there. And so if we define gj to be this thing here and capital Gji to be this inner product here, then this is the same as saying gj is the sum from I equals 1 to n, x tilde I gji, right? And so you can recognize this as a matrix multiplication, right? If we take g to be the vector whose coordinates are gj, x tilde to be the vector whose coordinates are xi, and g to be the matrix whose entries are gij, then we get vector g is equal to matrix g times vector x tilde, right? And so this is our desired system of equations. And then at this point, we can solve the system to get us our x tilde vector. So how do we actually solve that system? We're actually going to come back to that question in a little bit more detail. But for now, basically the answer is you hand it to MATLAB or you hand it to SciPy, right? So SciPy provides a function called linalg.solve, and you just provide it the matrix and the vector, right? You provide it capital G and little g, and it'll give you back x tilde. So just to make sure that everyone is following, the idea here is that so we're given the vector x, we're given all of these vectors bi, right? And we're given a function that calculates inner products in our vector space. And so we can calculate the coefficients little gj, and we can calculate the coefficients capital Gji. And so we can build this vector, and we can build that matrix. We can hand them to linalg.solve, and we can get the coordinates of the elements of the vector x tilde back in return. Right? So all right, so what if our set B is not a basis, right? So suppose we accidentally start from a set that isn't really a basis. There's two ways that it could fail to be a basis. One is that it could be linearly dependent, right? A basis has to be a linearly independent set. And the other is that it could be too small a set. In other words, there could be vectors in V that are not expressible as a linear combination of elements of our supposed basis. And we'll get different failure modes in those two cases. So in this first case, when we have a linearly dependent set, the most typical failure mode is that we'll get a division by 0 in our software library that we use to try to solve our system of linear equations. And that's good because it's like it's not a silent failure, right? It's you know, our program actually dies with a division by zero exception. Sometimes our library might try to be clever and, for example, drop vectors from our supposed basis until it really is a basis, meaning that we just assign them zero coefficients. That's usually okay too, because we'll still get our equation that x is equal to the sum of x tilde I bi. Just that some of the coefficients will be always zero no matter what x we pass in. The worst thing that can happen is that the library could fail silently if we give it a linearly dependent set instead of a basis. So due to numerical problems that it doesn't catch, it thinks it's found the correct x tilde, but due to numerical problems, we don't actually have the equation that we wanted, that x is expressed as a linear combination of the basis functions. So that's bad and we want to catch it. The other potential way of failing is that we might have given a basis that doesn't actually have the ability to express x, right? And in that case, we will always get a silent failure from this method. We will always will be able to calculate capital G and little g, and we'll always get back a vector of coordinates, but the vector of coordinates won't satisfy the equation. If we write R for the so-called residual, the difference between the vector we want and the actual vector we get as a linear combination of our basis functions, that residual will be non-zero. And so in both of these cases, right, in the numerical problem due to linear dependence, or in the case where we didn't give it a big enough basis, we'll get that the residual is non-zero. And so it's always wise to check your residual and make sure that it is zero, or at least close enough to zero for numerical precision, so that you catch failures. Now, this second case is actually useful if we invoke it intentionally, right? So if we, it makes sense actually to intentionally give our software a set of vectors that whose span does not include x, and then what we'll get is, as the output of our set of linear equations, it turns out that what we'll get is the best possible approximation to x. In other words, the vector out of all of the vectors that are representable as linear combinations of elements of B, we'll get the one that has smallest residual. And that's useful as long as we know that that's what we're getting, right? If we expect to be able to represent x exactly and depend on that later, that could be a problem. But if we say, okay, I just want the best possible representation of x and I know it's not going to be perfect, then it turns out that the same method will actually find that for you. We're not proving that here. We might prove that later in the course. But it's worth knowing that that's something you can do. Okay. So what exactly, somebody's asking a question on Piazza, what exactly is tilde x in the example? So let's go back to our original set of lecture notes here, right? So this is x versus tilde x, right? So x is a vector in our vector space. It's representable as a linear combination of basis vectors. Tilde x are the coefficients of that linear combination. And so if you string them together, they're a vector in Rn if we have a basis of n elements. Somebody wants to know where you get the residual from, right? And so here's the definition of the residual, right? R is just the difference between x and this linear combination of vectors. And so these are all elements of a vector space. And so by assumption, by saying that they're elements of a vector space, that means that we know how to scalar multiply and add and subtract them, right? And so that means that this expression here is something that we know how to compute, how to work with. And so we can actually compute the residual if we want to, right? In particular, you know, we might have, you know, this expression here is a vector in our vector space V, and so we'll be able to take its norm by taking its dot product with itself and check whether that norm is 0. And if that norm is non-zero, then we know that we failed to get a 0 residual. Okay. Oh, and somebody else wanted to know in this example why these two representations, why these two coordinate representations are the same. That's not actually obvious. The reason that I realized that they're the same is that we know that I3 applied to x is x, right? And so if we represent both x and I3 of x in our basis B, right, we know that I3 of x has to have the same coordinate representation as x, and so the only way to get that is by using this coordinate representation, the identity matrix. That's the only 3x3 matrix where if you multiply it by any vector, you get the same vector back. The interesting thing is that that is true as well in B prime, right? If we represent both x and I3 of x in B prime, then the coordinate representation of the identity has to be this again, because we put in one coordinate representation, we got to get out the same, put in one coordinate representation, we got to get out the same coordinate representation at the end. So let me, I can actually say this in a little bit more detail. So I should say in B comma B, right? Meaning that both the input and the output are represented in basis B, right? And then here, this is in B prime comma B prime, right? And maybe an interesting, a more interesting example would be, let's say, if we represent the input in B and the output in B prime, right? So we don't actually have to use the same basis for the input and the output. In that case, I3 tilde is a matrix which is not equal to the identity matrix. And I'm not going to try and calculate it on the fly, but here what we're doing is we're essentially changing coordinates, right? And so the matrix, it's the identity map, but the coordinate representation of the input is different from the coordinate representation of the output. And so that would be an example where we get a representation of this identity operator that is not the same as this identity matrix. All right. So let's go back. All right, we talked about coordinate representations of vectors and matrices. Let's talk a little bit about some other operations that we can do with matrices. So slicing is a useful operation that we can do only with the coordinate representation. What slicing means is to cross out some rows and columns of a matrix or of a vector and keep the remaining ones. So here's an example, right? So if we have L tilde 1, 2, 3, 4, 5, 6, 7, 8, 9, and we want the first and third rows and the first and second columns, right? We'll cross out the second row, the 4, 5, 6, and we'll cross out the last column, the 3, 6, 9, and we'll get 1, 2, 7, and 8 remaining, right? And so that this is a slice of this matrix. And we'll use a notation for slicing. 3:5 is the indices from 3 to 5, and 1:2:7. 2 is a skip, and so this is 1, 3, 5, and 7. So that's just a useful operation that we'll use sometimes. Maybe some more important operations we'll discuss in the remainder of the notes. So the first one is the adjoint of a linear operator and the transpose of a matrix. So transpose and adjoint are related. Transpose is an operation that you do on matrices, and adjoint is an operation that you do on linear operators. And just like every matrix can be represented, every matrix represents a linear operator, and every linear operator can be represented as a matrix, the transpose on matrices does the same thing as the adjoint on linear operators. So let's go ahead and say that in a little bit more detail. So let's say we have a linear operator L, which goes from vector space U to vector space V. We'll define another operator, L adjoint, which goes from V to U, so the reverse direction, by this equation. So the equation basically says that if you take the inner product between Lx and y, so Lx and y are both elements of V, and so I've put a subscript here to say that that's the inner product in V that we're looking at. And then if you take the inner product in U of x and L adjoint of y, right? So those are both elements of U. This inner product has to be the same as that inner product, no matter how we chose x and y, right? Now it's not obvious from the definition, but the adjoint operator always exists and is unique. For every L, there's exactly one L star. And so it makes sense to ask, what is the coordinate representation of L star? And it turns out that if you have a coordinate representation L tilde of L, then the coordinate representation of L star, of the adjoint, is just the transpose of the coordinate representation of L. In other words, I mean, here's the definition of the transpose, but basically the columns of L tilde transpose are the rows of L tilde and vice versa. So adjoint and transpose themselves are operators, right? So adjoint operator maps linear functions that take u to v to linear functions that take v to u. And the transpose operator maps m by n matrices to n by m matrices. And these are in fact linear operators. So for example, the adjoint of a plus b is the adjoint of a plus the adjoint of b. Let's see, adjoint and transpose both are their own inverses. In other words, if you take the adjoint twice, you get back to the original operator, and if you take the transpose back twice, you get back to the original matrix. If the two vector spaces are the same, right, so if you're looking at a linear operator that maps Rn to Rn, or a square matrix, an n by n square matrix, then you could have that linear operator be self-adjoint, and you could have the matrix be symmetric, meaning equal to its own transpose, right? And self-adjoint, because adjoint on operators is the same as transpose on matrices, self-adjoint operators correspond to symmetric matrices. And that's assuming that you use the same basis representation for the input and output vector spaces, right? So in other words, we don't just have to have u equal v, the input equal the output vector space. We have to take the same basis for both u and v in order to have self-adjoint operators turn into symmetric matrices. All right, so we can define an inverse both for matrices and for linear operators. So let's start with a linear operator that maps u to v. So L inverse also maps v to u, just like the adjoint. The inverse and the adjoint are distinct, but they have the same input and output vector spaces. L inverse is the inverse of L if it satisfies that for any two vectors x and y, if x is equal to L inverse of y, then y is equal to L of x, and vice versa. You can also write that as follows. For all x in u and y in v, x is equal to L inverse of L of x, and y is equal to L of L inverse of y. So unlike the adjoint, the inverse does not always exist. If it does, we call the operator invertible. And for invertible operators, if you take the inverse twice, you get back to the original operator. The inverse can only exist if the two vector spaces have the same dimension. If they have different dimensions, we might still be able to find what are called a left inverse or a right inverse, which are basically things that satisfy one or the other of these two properties, but not both. Right? So I just wrote those again here. Not invertible, another word for that is singular. And so for singular matrices, we can define what's called the pseudo inverse, which is basically like the inverse whenever that makes sense. And we write it as L with a dagger superscript. So L pseudo inverse is defined to be the operator such that if we take x equal L pseudo inverse b, then the residual Lx minus b is as small as possible, right? And so the set of lecture notes that I just went through says how to calculate the pseudo inverse if we have basis representations for our input and output vector spaces. All right, we can define, just like the inverse on linear operators, we can define an inverse operation on matrices. It satisfies essentially the same set of equations. And as you might expect, matrix inverse and linear operator inverse are related. If you have a linear operator L whose coordinate representation is L tilde, and if you take the linear operator inverse to get L inverse, or if you take the matrix inverse to take L tilde inverse to get L tilde inverse, then L tilde inverse is the coordinate representation of L inverse, right? So you can do the inverse directly as a linear operator, or you can map to a coordinate representation, take the matrix inverse, and then go back to a linear operator. And similarly, there's a matrix version of the pseudo inverse, and there are algorithms for calculating these matrix versions. You'll find them in numerical libraries like MATLAB or SciPy. All right. It's going to be useful as well to talk about patterns that a matrix can satisfy. So the linear operator, right, is an abstract thing. It is the same no matter what coordinate representation we pick for it. But some coordinate representations are going to wind up being more convenient to work with than other coordinate representations. And so it's going to make sense for us to pick a basis that makes it easier for us to do operations that we have to do. So in particular, it's often helpful to have the non-zero entries of our coordinate representation matrix follow some kind of simple pattern. So I'm going to talk now about a few different patterns that they might follow. So the first one is a diagonal matrix, meaning that you have zero entries everywhere that's not on the main diagonal and non-zero entries everywhere there are x's, or potentially non-zero. It's okay to have a zero entry on the diagonal, but it's not okay to have a non-zero entry off the diagonal. Right? Slightly more general than diagonal is lower triangular. So here's a picture of lower triangular, but it means that all of the non-zero entries fall on or below the main diagonal. Similarly, there's an upper triangular matrix, which is the transpose of a lower triangular matrix. And the absolute simplest pattern is the identity matrix, which is this matrix right here. It has ones on the main diagonal, so it's a diagonal matrix, but it's even more constrained than a diagonal matrix because all of the diagonal entries are the same and they're equal to 1. And then a slightly more complicated pattern is just what's called a general sparse matrix. That means that there's a lot of entries that are zero, but not in any particular pattern. And so, a typical sparse matrix might have a very high fraction of zero entries. It might be that 90% or 99% or 99.9% of the elements are zero. And so for all of these patterns, the reason that they're computationally easier is that we don't have to work with any of the zero entries explicitly, right? So if we want to, for example, multiply by a general matrix, we have to touch every entry in the matrix. But if we want to multiply by a diagonal entry, we only have to touch the diagonal. If we want to multiply by a diagonal matrix, we only have to touch the entries on the main diagonal. And so there are, in Rn, there are going to be n squared entries in the matrix, but there's only n entries on the diagonal, so it's going to be much faster to work with. All right. Right. So somebody's asking again about the relationship between inverses in linear operators or inverses in matrices. So I think a diagram is helpful. So let's say that we have a linear operator and we have a matrix L tilde, right? So the operator is L and the matrix is L tilde. And so these two are related by being a coordinate representation. Right? And so you can go back and forth between L and L tilde, right? L is the operator and L tilde is the matrix, right? And so I'll just write over here, L is in the set of functions that map a vector space U to a vector space V. L tilde is in R n by m, right? So we can go from an operator L to the operator, let's say L adjoint, right? And so this is the adjoint relationship, right? You can go back and forth between L and L star, and you can go back and forth between L tilde and L tilde transpose, right? So this is the matrix transpose, right? And the point is then that these, again, satisfy the same relationship. One is a coordinate representation of the other. Right? So you can go around this diagram in any order that you want, right? So you could start with a linear operator, you could get its coordinate representation L tilde, transpose it, and then go back to find the operator whose coordinate representation is L tilde transpose, and that operator would be L adjoint, right? Or you could take your operator and take its adjoint, find its coordinate representation and transpose it, and you would get L tilde, right? So the point is that linear operators are the left side of this diagram, matrices are the right side, and you have corresponding operation, adjoint on one side and transpose on the other, that do essentially the same thing, but on these different entities. And then the same thing is going to be true, right? So you can do L to L inverse to L tilde inverse to L tilde, right? And you can go around that same diagram in any order. Right? So hopefully that is helpful. Someone is asking why matrix patterns are important. Is it just computational efficiency? Chiefly computational efficiency is the reason that they're important. There are cases where you can tell something interesting about a matrix by its matrix pattern. So we had an example actually a few lectures back where we could tell, for example, when a variance matrix was diagonal, that told you something about the shape of a scatter plot of vectors from the distribution, right? If you had a distribution over vectors in Rn, and if you took its variance matrix and you looked at that variance matrix, if it was diagonal, that told you something about the shape of that distribution. So I would say that the key thing about matrix patterns is the computational implications. But there are some times when you can tell something interesting about some process by looking at the pattern of some matrix. All right. A couple of last properties that a matrix can have. Let's take some inner product space V, right? And we'll have two vectors x and y, and they're called orthogonal if their inner product is 0. And so orthogonality is important geometrically because orthogonality in a vector space is basically the analog of being at right angles, right? So if you have two vectors in Rn that are at a right angle, you can prove that their inner product is, their dot product is 0, and that generalizes to arbitrary vector spaces. We say that two vectors are orthogonal or at right angles if their inner product is 0. An orthogonal matrix is a matrix whose columns are orthogonal to one another, right? So if you take the matrix and extract each of its columns as vectors, call them AI, right? Then AI inner product AJ is 0 whenever I is not equal to J. And if A is orthogonal and square, then A transpose turns out also to be orthogonal and square. If A transpose time, columns being orthogonal means that A transpose times A is going to be diagonal. You can work that out by the fact that the ij entry of A transpose A is the dot product between the I column of A and the j column of A. And so we know that that's non-zero only when I equals j, and therefore only the non-zero entries of A transpose A, only the diagonal entries of A transpose A can be non-zero. If A transpose A is the identity, meaning that the columns are orthogonal and each column has norm 1, that's called an orthonormal matrix. An orthonormal matrix is, of course, orthogonal, and every column has unit length. And if A is orthonormal and square, so is A transpose. And a useful fact is that the inverse of an orthonormal matrix is the same matrix as its transpose. That's obviously not true of general matrices, so it makes it much easier to calculate the inverse of an orthonormal matrix. All right, and a last useful property of operators or matrices is positive definiteness or positive semi-definiteness. These are two related properties. So let's say we have a linear operator which maps a vector space U to itself. Let's say that the inner product between x and ax is always non-negative. In that case, the operator is called positive semi-definite, and it's called positive definite if the inequality is strict. In other words, x dot ax is bigger than 0 for all vectors other than the 0 vector. So that's a linear operator, and as always, there's a corresponding concept for matrices, and it's actually called the same thing. So a positive definite or a positive semi-definite operator, if you take its coordinate representation, that'll give you a positive definite or a positive semi-definite matrix. If a matrix happens to be symmetric, or alternately the operator happens to be self-adjoint, it turns out to be easier to test whether a matrix is positive definite or positive semi-definite. And symmetric or self-adjoint operators or matrices that are positive, definite, or semi-definite, these come up a lot in applications, and so it's a useful property to be able to work with. So, oh, we have a question now back about this algorithm for, where did it go? The algorithm for calculating a coordinate representation, right? And so our assumption is that we're given a vector x and we're given a basis, meaning a list of vectors b1 through bn, and we're given the ability to compute dot products among vectors. And then given all of those things, we want to compute the coordinate representation. And so we've defined little g and big G in terms of inner products between vectors, right? Here's the definition. And so by assumption, we're able to calculate little g and big G. And then given that, we can do this solving a system of linear equations to get x tilde. All right, so so the next set of lecture notes is about how to solve linear equations, but I think rather than going to that next set of lecture notes, what I want to do is go over a useful example. So let's take a look here. So what I'm going to show, so I'm going to play this. I'm going to play this video, but you can also download the video and play it yourself anytime you like. So what I'm going to do, I made this video to try and help people get more familiar with these operations that we can do on vectors in the unusual vector spaces that we gave as examples. And so what I'm going to do here, I made the video to show the operation of an algorithm that we're familiar with in a vector space that we're less familiar with. So the algorithm is the Perceptron algorithm. So actually, before we go through the video, just remind you what the Perceptron algorithm is, right? So we have a linear discriminant function, right? So it is the inner product between w and phi of x, right? X is one of our input vectors, and phi is a feature function applied to that input vector, and w is a weight vector, right? And we would like that to be bigger than or equal to 0 if and only if x is a positive example, right? So that's our goal. And the Perceptron algorithm, it just it repeatedly sees x1 and the label of x1, which I'll call L1, x2, L2, and so forth. And it on xi, it predicts the sign of w inner product with xi, right? So it initializes w to 0. And then on a mistake, if Li is positive, right, +1, it will say that w, we'll make a colon equal for assignment, w gets w plus phi of xi. So I forgot to write phi here, so let's just there, sign of the inner product between w and phi of xi, right? And then if Li is equal to -1, then W is assigned to be W minus phi of xi, right? So this is the perceptron algorithm. And this algorithm, when we first saw it, we were looking at it in the in a real vector space, right? Phi of xi was going to be an element of Rn. So what I want to do is show you the example when phi of xi is actually something in a different function space that's not just a real vector space. And in particular, I'm going to use this example where so in our example, it's going to be the case that phi of xi is equal to q sub xi, right, which is the function. So q sub xi of x is defined to be e to the minus difference between xi and x squared over 2 sigma squared. And sigma squared is a parameter that we fix ahead of time, right? So here, phi of xi is just a function in a vector space of functions, and it is this particular function, the one which when you apply it to x gives you sort of a Gaussian bump centered at xi. All right, and so I'm going to run now this perceptron algorithm in that function space. And so what that means is that when I make a mistake, I'm going to take my W is going to be initialized to the 0 function, right? The inner product between W and phi of xi, we defined in our definition of this function space, we defined that inner product to be W evaluated at xi, right? So we're just going to that inner product, when we defined this function space, we defined that inner product on it. And so if we evaluate W at xi, and if it has the wrong sign, then we're going to add a Gaussian bump centered at xi, which is going to make it larger, or subtract a Gaussian bump centered at xi, which is going to make it smaller. And so you can see that the function that we're working with is going to do better and better at becoming a discriminant function. So here's what that looks like. Let's make it bigger, right? So let's actually go back a little bit, right? So here is our first training example, and we added a Gaussian bump centered at that training example, right? Subtracted a Gaussian bump centered at that training example because it's a negative example. And now the discriminant function is negative here, and so we're not going to change anything. There is a positive training example, and the discriminant function was negative, so we added a Gaussian bump centered there, and now you can see the decision boundary here between this positive example and that negative example, right? And if you keep on going forward, you'll see another example that we made a mistake on, and we keep adding these Gaussian bumps, right? We don't always add Gaussian bumps, we only add them when we make a mistake, right? And it animates how the discriminant function changes. And you can see that, you know, if we pause now, right, we're actually doing a pretty good job of having the discriminant function be positive on the positive examples and negative on the negative examples. All right, so let's continue playing this. And what will happen is that by the end of the video, we will have actually managed to get all of these examples classified correctly, meaning that the discriminant function will be positive on the x's and negative on the o's, right? And we're doing that by running this perceptron algorithm in this weird vector space where the elements are functions. So you know, please watch this video over again if it didn't make sense the first time, and please ask us questions. There are all right. There there's a couple more questions on Piazza, but they look like they're questions that we can answer better in text. And so I think now is probably a good time to stop the lecture. I'll let this video run to completion, which I think it basically has. Oh no, we're almost there. All right, now I think we've got, we've got every example correctly classified, right? And so we're done. And you can see that we've learned a discriminant function that, the dark line is the zeros of the discriminant function, the blue are negative, and the green and yellow are positive. So you can see that the Perceptron algorithm has actually worked, even though we ran it on this weird vector space where the elements are functions instead of on Rn. All right, so I think that's a good place to stop. We will continue next time around, and as a reminder, we are likely to release at least one assignment later today, so keep your eyes out for that.